Okay.
Hello everyone and welcome to the Geoscience and Geoenergy webinar on the 28th of April 2022. My name is Christine Meyer, I'm a postdoctoral researcher at Unicamp in Brazil, and together with Sebastian Geiger, who is a professor at TU Delft, I have the pleasure to co-host this webinar today. Today is the 101st lecture of this webinar, and I'm delighted to welcome Ronny Pini as our distinguished lecturer. Ronny is a reader in chemical engineering in the Department of Chemical Engineering at Imperial College, which he joined in 2015. He received his master's in 2004 and his PhD in 2009, both from ETH Zurich in Switzerland. He worked as a postdoctoral scholar at Stanford University in the Department of Energy Resources and Engineering. His research combines experiments and models to study the fundamentals of reactive flow and transport processes in porous media, with applications ranging from geoenergy applications to industrial gas separations. A major focus of his research is reducing CO2 emissions from industrial processes, including oil and gas extraction from the subsurface and power generation by incorporating technologies such as carbon capture and storage. The title of his talk today is Chemical Transport in Disordered Porous Media. Thank you, Ronny, for accepting our invitation, and to the audience. As usual, please note this lecture will last for about 30 minutes, followed by questions, by your questions. Like always, type your questions in the chat box, and Sebastian will go through them and share the discussion session afterwards. Feel free to type your questions at any time during the talk, as this might trigger further questions from the audience. And now, Ronny, the floor is yours. Looking forward to your talk.
Thank you. Thank you, Christine. Thank you, Sebastian, as well, for the kind invitation. It's really a great seminar series, and I'm very happy to have the opportunity to contribute to it. So I hope everybody can hear me well, and you can see my slides and my pointers as well. And as Christine said, so the title of my presentation today is Chemical Transport in Disordered Porous Media. So you will see I'm going to present results regarding the transport of chemicals in rocks, and rocks comes to us with all this disorder in their properties, and that's what we try to understand as we try to indeed describe transport in these systems. So before I start, I just wanted to acknowledge, the people who have done the work that I'm going to show today. So there's a number of PhD students and postdocs who have been working with me here at Imperial in the last few years. Also, a few collaborators, which actually helped really a lot in some of the studies that we are carrying out at the moment, and also obviously acknowledging all the funding agency that were so kind to fund the work and allow us to do the research we want to do. So we indeed we are interested in the transport of chemicals in porous media, and the reason is that transport underpins many applications in the subsurface, and one of them is shown in this cartoon is the geological storage of CO2 in deep saline aquifers. So that's a technology that I don't need to discuss in detail to this audience, as I'm sure everybody is well aware about it. And so once you inject CO2 into this porous formation, there is a lot of great science, let's say, that can take place. We're dealing with multi-phase flows and complex fluid mixtures and complex rocks. And a lot of this science and results have been discussed as part of this seminar series in the past presentations. We are particularly interested in the process that takes place after the CO2 has been emplaced and has been trapped, for instance, by capillary forces. So we're very interested in the process of the dissolution of CO2 into the brine, and then the subsequent mixing and dispersal of this CO2-rich brine into the aquifer. So this is obviously a very important process because it removes the CO2 from buoyant gas phase, but also because it allows occupying more effectively, let's say, the pore space of the aquifer that we are considering. And so natural convection in this system actually can greatly enhance the mixing process of this CO2-rich brine. And this is mainly driven by two processes. You can have convection that is driven by a pressure gradient. This is because you typically have some groundwater advective flow in the reservoir. But this can also be driven by changes in the density of the fluids that are essentially generated once the CO2 dissolves into the brine. And this creates some instabilities, which further enhance the mixing of the brine of the CO2-rich brine with fresh brine. And so both of them are very important because, as I said before, they basically remove CO2 from a buoyant gas phase. So we are interested in understanding the transport. Therefore, this is truly a fundamental process that takes place also in CO2 sequestration, because eventually transport is what drives reactions in the fluids, which eventually will take place. Now, the challenge for us in describing, understanding transport in this system is that we are dealing with a natural system, and mentioned in my title, these are rocks which are disordered by nature because they have spatial variability of the chemical properties and physical properties. And this variability starts already at the scale of the samples that we use in the laboratory. That's where basically the fundamental processes of mixing and reaction take place. So you see here an image is a three-dimensional reconstruction of the porosity that you can obtain, for instance, by X-ray computed tomography of a carbonate rock. You see the colors here refers to porosity. So in yellow, you have regions of high porosity, and in gray, dark gray, you have regions of lower porosity. So you see that there is quite some variability in the sample. You don't see much correlation as well. So the system is indeed quite disordered. If you focus in one of these small elements, you can obtain higher resolution images, and you see that this disorder continues, right? And here it goes down to the scale of individual pores, where you can see a strong variability in both the shape, the size of these pores. So all this complexity, this heterogeneity leads to essentially, as far as transport is concerned, to a very complex velocity field that is generated once you flow a fluid through the rock. And in turn, this generates a very complex evolution of the concentration of reactants in your rock, right? As a result of this variation in the velocity. So our efforts in the last few years have been focusing on developing laboratory protocols where we can not only resolve and quantify these heterogeneities, but also to unravel or to measure and to observe the evolving concentration of species as they've been transported in the medium. So to appreciate the complexity of the problem, but also why it's beneficial to be able to observe transport directly in porous media, I wanted to start by showing these results for a fairly simple, let's say, experiment. So we prepared a sample using beads, and we prepared it in the way depicted here. So we had the central part of the sample being packed with some smaller beads, while the annulus of the sample was packed with some beads with larger diameter, right? So this would result in the central section of the rock, of the porous medium, of having a low permeability, while the outer edge would have a higher permeability. What we've done then is we've done a tracer experiments, specifically echo experiments, meaning that we have injected a tracer in the left-hand side of the sample, and after the tracer has traveled a given distance into the sample, we have reversed the flow direction and we draw the tracer. I will talk later about the technique that we use to image the transport. I just wanted to discuss briefly what we observed. So you see here now what happens to the tracer plume as it's being injected. So you see that indeed the outer edge, you have a faster movement of the tracer, which eventually detaches from the central plume. And essentially we describe these as two different mechanisms. So the first one is spreading. And the spreading is really the stretching of the plume, which is caused by this, let's say, macroscopic velocity heterogeneities, the low versus the high permeability layer. It doesn't necessarily lead to a better mixing. It just simply stretch by advection the plume. And the result is that you're enhancing concentration contrast between the tracer plume and the rest of the system. The other process is dilution or mixing. This takes place in both plumes, and this is really the process of mixing. So there you do increase the volume of the plume as it travels, for instance, by diffusion, and the role of mixing is indeed to reduce concentration contrast. And indeed, you see the reduction in color of the plume as it travels through the rock, and this means the concentration gradient are being removed. So what you observe also is that upon flow reversal, you can actually recover the component of spreading, right? You can see that the plume gets compact again as before leaving the core, while dilution keeps going because this is an ubiquitous process. So you see that there are very different processes acting over different time scale and length scales. And you can imagine that in a rock sample, both of them will take place, but in a less, let's say, ordered manner. So when you perform experiments in the laboratory, you do a similar experiment, right? You have your rock sample, and you perform what we call a tracer test. So your rock sample is saturated with the water. You inject a pulse of a tracer, and then we measure a breakthrough curve. And the breakthrough curve, we use it to infer the mechanisms of mass transfer that happens in the sample. So to interpret this breakthrough curve, you need a model. And the two ingredients of this model are models for the transport of the chemical species, right? So the concentration variation in time and in space. But you also need, ideally, a flow model that indeed captures the variation in velocities within the rock sample itself. So typically, though, the model is reduced to a very simple, to a much simpler formulation, which is the advection dispersion equation, where now you work with an average fluid velocity, and you describe dispersion using a Fickian term, which uses a so-called dispersion coefficient, which is some sort of an upscale diffusion coefficient. And this dispersion is what is typically used as a fitting parameters to describe the experiments. Now, when you try to apply this equation, the advection dispersion equation, to tracer experiments in rock, what you observe is that actually doesn't really work well. It's too simplistic. And so over the years, more advanced models have been introduced. Some of them are mentioned here. So the multiple rate mass transfer model. So you extend this advection dispersion equation with additional mass transfer mechanisms. And also the continuous time random walk model, which is a more general, let's say, approach, stochastic approach to describe transport, right? And also these ones are typically applied in one-dimensional form. So you assume that there are heterogeneities in your medium, but they are fairly uniformly distributed. So now the key is that these models, these more advanced models that we need, do introduce also additional parameters that needs to be identified. And so it's very important when one's design an experimental campaign to cover a sufficiently large range of flow rates, so to measure multiple breakthrough curves at different flow rates, so that you can reliably calibrate these models to obtain reliable estimates of these parameters, because you have many more parameters. Some mechanism might actually lead to the same macroscopic effect. So it's very important to not limit yourself to individual flow rates, as you might not be able to properly estimate all these parameters. So now we'll start showing you some results that we obtained. And so these are indeed results of unidirectional tracer tests, such as those that I described before, in a water-saturated rock using a conservative tracer. And so this is a set here on the left, a set of breakthrough curves that we measure at different flow rates. You see 5 different breakthrough curves. So to interpret the data, we use the concept of residence time distribution. So we apply some normalization to these breakthrough curves. So we apply normalization that, we normalize the data by the amount of tracer injected, but we also use the mean residence time of the tracer in the rock as a factor to normalize the data. So we then basically convert this set of data into this form here. And you can see that the effect of the normalization is quite interesting. So suddenly now all these 5 curves collapse into a single universal curve, right? And this is a nice symmetric breakthrough curve. The maximum is fairly close to the mean residence time. The curve is also fairly narrow. So this is a sign of a fairly uniform system where the advection dispersion equation would, in principle, work. And indeed, we know that Bentheimer-Sandstone is a is indeed a fairly uniform piece of rock. But we have done a systematic study, so we expanded the study to include different type of porous media. So here on the left, you see a bit pack, a random bit pack. So you see similar effect of the normalization. That you see this very nice symmetric curve. We have various flow rates here, but they all collapse into an individual universal curve, which is nicely centered around the mean residence time. And at the bottom, we see results from two different carbonate rocks. So Edward Browns here on the left and Ketton limestone on the right. So suddenly now with the carbonates, you see a different story. So the curves are much more, they're much wider. They show some earlier breakthrough. They show also some long time tailing, very, very clear also for Ketton. But you also see that they no longer collapse into an individual curve, right? And particularly at the late times, you see the different curves at different flow rates diverging from the main trend. So this is an indication that advection dispersion equation will not work here, but also that there are some other mechanisms, mass transfer mechanisms at play that are basically acting during the transport of the solute through in the rock. So we can start making hypotheses of what are these mechanisms or what is the origin, let's say, of this deviation, and we can do that by providing some characterization of the sample. So here on the left now you see the porosity maps that we obtained by X-ray CT scanning of the three rocks that I was considering, the Bentheimer sandstone, Ketton, and Edwards Brown. And so the porosity map already reveal indeed that there is a significant increase in the, let's say, heterogeneity pattern of the porosity as we move from Bentheimer down to the carbonates. So here this is reminiscent of what we were discussing before as an increased extent of spreading when mass transfer is concerned. When we do some higher resolution analysis of these samples, we can go down to the size of individual grains and observe grain size distributions. And here what we see, or what we can extract from these images, is that we know that in the carbonates, there is a significant amount of micro porosity, or let's say porosity below a given size of pores where transport by advection is quite limited, and most likely will be dominated by diffusion. So the degree of this sort of submicron porosity increases as we move from the sandstone to the carbonates. And so both of these aspects, so the submicron porosity and the subcore scale porosity heterogeneity, will play a role in the interpretation of this data. So as I said before, you measure breakthrough curves and you need a model to let's say obtain useful parameters. And we decided to use the continuous time random walk model for that to capture, this multi-scale porosity heterogeneity in the system. So we decided to use a one-dimensional formulation. Here you see the equation in the Laplace space. This is something that was introduced by Berkowitz and co-workers. And the continuous time random walk model describes transport as a stochastic process of displacement events in time and space. And at the core of the formulation is this function here, is a memory function. And the memory function basically describes the variability, or the distribution of the transition times of the solute in the porous medium. And there you have a flexibility to choose which memory function you want to adopt, depending on the type of mechanisms you want to describe. So we decided to compare two different memory functions, also as an educational exercise for us, as this model has not been widely applied to rocks, so there was something to learn as well, also regarding the parameters of this function. So we used a memory function that describes a single rate mass transfer process. Here is where you divide your pore space into a so-called mobile pore volume fraction and the immobile pore volume fraction, where you have more stagnant zone. And this is this parameter theta, and the parameter T2 basically define the release time from these temporary traps in the immobile regions. The second memory function is a more general description of transport, and uses a truncated power law to describe the variability, let's say, of these transition times. So essentially, you use two timescales. One is the advective timescale. The other one is a so-called cutoff timescale. It's related to diffusion. And there is a beta parameter that describes heterogeneity of the system, which essentially describes the variability of transition time between these two bounds, between T1 and T2. So we identify those parameters that we thought are global, so depends only on the rock. So this might be, for instance, the fraction of immobile pore space and or the heterogeneity factor, and also the others that are flow rate dependent. And so we went and we applied this model to our breakthrough curves. And this is something you can also, there is a MATLAB toolbox that was also produced by the group, that also allows for an easy application of the model to your experiments. So these are the results. So you see now the plots I've shown you before for the 3 rocks. And now the lines are indeed the fits obtained using the continuous time random walk model. So I'm showing you only here one set of lines. This is the one that we obtained with the truncated power law. But I have to say that both memory functions provide an excellent fit. So you cannot really distinguish between the two. What we know, though, is that the advection dispersion equation had a hard time indeed describing the curves, not surprisingly, for the carbon in particular. So I'm reporting here a few parameters that we obtained. So one, particularly the global parameters. So I'm showing here the dispersivity, which is a characteristic length scale for the mixing process that we obtained for the 2 formulations. And we see that they're consistent in providing the same trend. So we see an increase in dispersivity when we move from the sandstone to the carbonates, a significant increase, and in both formulations. So that's not surprising as we move from sandstone to carbonates. For the truncated power law, as I said, there is this beta parameter, which is also a global parameter and describes the heterogeneity of the system. And we see that indeed it follows the same trend. So with decreasing beta, you increase, let's say, the variability of transition time and therefore the extent of heterogeneity of the system. And this is consistent with some of the early observation of applying this model to some porous media. So I wanted to spend one slide on discussing this issue of using one single dispersivity coefficient. So we decided to indeed use one dispersivity coefficient that for each rock. And this basically implies that when we report our data using these classic plots, so the dispersion coefficient as a function of the Peclet number, so is a way to, let's say, scale dispersion data, we see that they follow a linear relationship with the Peclet number. So this is quite a simpler way to describe dispersion, and it's therefore good news. And the only scaling parameters that you need is this so-called inhomogeneity factor, so this sigma parameter, which moves the curves up and down depending on the dispersivity of your system, right? And we see indeed that the sigma parameters increases, again, moving from bead packs to sandstone to the carbonates in the same order that we observe the parameter beta to change. So this is one confirmation that even for rocks of different types and with different textures, we can still adopt a fairly simple correlation to describe the dispersion coefficient, which you need to describe mixing in these systems. Another parameter that we obtain from the fitting of the curves is the fraction of this immobile or pseudo-immobile pore space where mass transfer is limited most likely by diffusion rather than by advection. And we had some good results in the sense that the trends that we observe, where the Ketton limestone shows the largest and significant amount of this pore space, is in agreement with the independent data that we obtained by mercury intrusion porosimetry, which is a technique that you tend to use indeed to describe pore size distribution. So we have a fairly good agreement between the two sets of data, again indicating that the model was applied in a correct manner and provides some consistent results with what we obtain independently when we characterize these rocks. So the fact that we have this immobile or pseudo-immobile pore space, this means that indeed we are introducing some mass transfer limitation in our system, and this can be analyzed more generally in the context of what is typically referred to as anomalous transport, right? Which arises from the non-equilibrium between these two transport processes, the one by advection and the one by, let's say, diffusion, right? And so the truncated power law can give us actually insight on this. So we can actually use the two timescales of the power law, the truncated power law, to indeed identify the characteristic length scale of advection, but also the characteristic length scale of diffusion. And so here I'm showing just the plot where we see that for each rock we obtain an independent characteristic length scale for the advection process, increasing again from Bentheimer sandstone to the carbonates, not surprisingly. And we use then the T2 value to obtain the characteristic length scale for the diffusion process. And what we see is an interesting trend where the ratio between these two length scales actually define the strength of anomalous transport. So basically the difference between these two different time scales. So we see that the value is much larger than 1 for Bentheimer, while it's much smaller than 1 for Keton. And in this case, this means, therefore, one way to understand these results is that in Keton, diffusion is not able to keep up with advection, right? Leading to this situation of non-equilibrium, and therefore leading to this tailing in the curves and this divergence of the curve at different flow rates, because flow rate will obviously have a role to play relative to the diffusion process. So it's a very, I think, very good way to actually understand why anomalous transport is observed in these systems. Okay, so I mentioned before, so far we focused our analysis on the breakthrough curve, but I mentioned before that we can learn a lot by imaging the transport process directly into the sample. And so here we adopted a technique called positron emission tomography that basically allows us to observe the evolution of a tracer plume as it travels through the sample. And using this concentration, the evolution of the concentration of the tracer, we can, in a way also confirm, hopefully, some of the insights we have obtained from our modeling exercise. So for those of you who are not familiar with this technique, just one slide here. So this is a nuclear imaging technique. This is also a technique that is being used in the medical field, like for medical CT scanning. But here, the technique uses exploit the radiation of a positron emitting isotope. So essentially, there is a range of radio tracers that one can use. We mostly use these two. So this is a tracer that is soluble in water. You just need very small quantity of this tracer. And as the radio tracer decays, the decay process produces eventually gamma rays that are detected by a series of detectors, indeed, that are placed around the sample in an instrument that looks, very similar to, indeed, a medical CT instrument. So in essence, you record all these events, these gamma rays that hits the detectors over time, and you can use this detection to reconstruct the position of the tracer as it travels to the rock. So the technique is actually quite powerful because it provides you very high temporal resolution. So because you have a continuous recording of the entire field of view of your sample, so you don't need to move the camera and so on. But it has also a very high sensitivity. So we did a comparison, for instance, here of the same experiment carried out where we try to monitor the displacement of a tracer by X-ray computed tomography and PET. And you can see already from the images that the X-ray CT is affected by more noise, significantly more noise as compared to the PET, which provides much more clean images, which is indeed very important when you want to use the information to quantify the transport process. The resolution, the spatial resolution, is similar to it's allowing us also to map, let's say, the heterogeneity that we observe with X-ray CT to the transport experiments quite easily. So we have performed the same experiment, indeed, where we image the tracer that moves through the rock sample. You can see the 3 rock samples again here. And you just seen before indeed now you see it again, the plumes that travel through the sample. So I'm stopping the moving here, so just to discuss briefly in qualitative terms what we see. So you see indeed that in the Bentheimer sandstone, the plume stays fairly constant as it travels through the rock with fairly small or moderate mixing as it travels. While when we move to the carbonates, you see much more spreading, much more mixing going on. You see a lot of discoloring, right, of the plume, so much smaller concentration in Keton limestone, so a lot of mixing here going on. You can see also this plume here at the trailing edge that remains behind, and this as most likely to do with these microporous regions where the release of the tracer is much lower as compared to the advection part of the transport. While in Edwards-Brown we see more stretching going on, similar to the spreading that we discussed in our first slide with the random bitpack. So you see probably more stretching and spreading driven by heterogeneities in permeability and porosity. So the ability of having now, the opportunity that we have now having these images is that we can have a much more comprehensive analysis of the transport process, because we can use the concentration, the evolving concentration field to further quantify the transport process. And we started doing it more recently by computing the evolution of the spatial moments that we extract directly from the concentration plume as a function of time. So we focus on the first 4 moments. So the 0 moment is nothing else than a mass balance, let's say. This is 1, and as long as the tracer is inside the rock, and then once you have breakthrough, you start losing mass from the tracer, from the rock. The first moment is related to the position of the center of mass. The second is related to the variance, which is the spreading of your plume. And the third is related to the skewness, so how symmetric is the plume as it travels through the rock. And the fourth moment tells you something about the strength of the symmetry, right? So we started doing it with Bentheimer sandstone, and I'm comparing here indeed the data that we obtained directly from the PET images, which are the symbols, to what we obtain by predicting from the breakthrough model modeling that we have shown before, right? Using the CTRW model. And actually you see that indeed there is an excellent agreement between the data and the model, indicating indeed that here we are still doing a good job, even though we are still using a one-dimensional model to describe the transport process. So I'm sure you're thinking, well, what happens when you now consider the carbonates? And indeed, that's what we are currently working on. We have the data, we just need to complete the analysis. And so what I'm showing here on the right are just the comparison of the evolution of the moments at a specific flow rate for the Bentheimer sandstone in black, but also the 2 carbonates rock as predicted by the model. I'm not yet showing the data. We are not there yet. But the good news is that we definitely see that there is variation in the moments. So meaning that this can also be used, this information, to better understand the transport process. The question, though, is whether, by comparing these images now, the experimental one and the model prediction from the one-dimensional formulation, whether this is actually sufficient to capture actually the evolution of the moments in the rock sample, right? Because you can see there is obviously a lot of difference between the two. And my answer, I would say, or what I'm expecting, that most likely this will no longer be sufficient, but the model approach might need to be extended to account, indeed, for spatial variation in the porosity and permeability that would better capture the evolution of the plume as it travels through the rock. But we have the data to validate this, so that's work in progress. And indeed, reaching now almost the conclusion of my talk, I wanted just to discuss briefly what we are doing indeed already at the moment to try to extend these models to account indeed for heterogeneity in the transport properties within the core sample itself. So far we focused a lot on the transport part of the problem, but our intention indeed to extend this by also having a model for the flow. And a key input for this part is having a permeability map of the rock. And we started doing some work on how to obtain a permeability map of these rock samples. This is obviously a challenging task. That's not something easy to do, because particularly for carbonates, you cannot easily correlate, for instance, porosity to permeability, right? So you need to come up with some potentially other means to do that. So one option that we are exploring is to combine the transport experiments with two-phase flow experiments, gas and water displacement, drainage displacement, use them to quantify heterogeneities in the capillary entry pressure. That's something we have been doing as well in the past, and then create a link between the capillary pressure properties and the permeability map, which we think is a stronger link as compared to a link between a porosity and a permeability. So we started doing some work in this direction. The results are promising. So you see here the model prediction now when we use a permeability map and compared to what we observed experimentally. So we are slowly getting there. And this is indeed promising. And this will give us the opportunity to indeed continue the analysis I was showing before regarding the moments distribution. Another interesting way, this is my final slide, to obtain permeability maps is to exploit directly the information that is contained in the PET data, so the concentration evolution of the solute. So this work that is led by Chris Zahasky is a collaborator. We have been working with him since a few years now. And essentially the idea here is to indeed exploit the concentration evolution of the solute for the permeability inversion problem. I'm just providing a bit of information on how the process works, but in essence, what you can do is that, given that you have the PET images, for each voxel in the system, you can produce a breakthrough curve, and you therefore can use this information to extract what we call an arrival time, right? So you can define, in this case, the 0.5 quantile, so the time needed for half of the solute mass to have traveled through that particular voxel. And so for each of those voxels, we can define this arrival time. And the hypothesis is that this arrival time correlates to the permeability of the rock, the local permeability. And so what Chris has done with his student is to essentially perform a number of simulations of three-dimensional transport simulation for different synthetic permeability and compute the corresponding arrival time maps, and then use this to train a convolutional neural network that would then predict back the permeability. So they've run many cases, so to have a very solid training data set. And once you have the convolutional neural network trained, we can apply now the network to our experimental data. Here I'm just showing on the bottom, for instance, the map that we obtained directly from PET of the experimental arrival time, and then the corresponding permeability map that is then produced by the neural network. And you can then use this map to predict the arrival time using the model, and you see that it's doing a very good job. So that's another interesting way to deal with the problem of generating permeability maps of the sample that would then allow us to expand the problem of transport in rocks in a more comprehensive manner. Good. And with this, I would like to just draw a few conclusions for my talk today. So we are very interested in chemical transport because it's a fundamental process, has implication to many subsurface processes, including CO2 storage. When we started this work, we noticed that the literature data on the transport properties was largely scattered. So we decided to tackle the problem in a systematic manner. We developed some laboratory techniques supported by 3D imaging to indeed interpret the experiment and to better understand the transport process. And we noticed that the ability to directly observe the spatial structure of the concentration field in the medium is quite important to inform numerical models. You have seen an application just now, for instance, to produce permeability maps. And this would allow us to indeed have an integrated workflow to interpret these experiments and to characterize these heterogeneous rock systems. And once you have this toolbox, let's say, you can tackle many more complex problems. We are very interested to obviously extend the work to have also chemical reactions taking place, also transport in situation where you have multiple fluid phases in the system, or even transport of more complex species such as colloids. There's definitely a lot that can be done, a lot of research that can be done, and this is exciting. So this is my last slide. So thanks again for your attention, and I'm happy to answer or take questions.
Thank you.
If you need to stop sharing, or if it's
yes,
okay.
to unshare your slides. Okay. Thank you very much for a really nice talk, Ronny. Fantastic work to see how you're trying to correlate the flow field, the concentration field to the permeability field, because I understood this has been sort of not the holy grail, but one of the big unresolved issues in all the stochastic hydrology modeling work. We do have some questions coming through, so I start with one from Julian Mays, who asked, thank you for the great presentation. When early on you said that the advection dispersion equation failed, was that with a constant dispersion coefficient? Do you match the experiments if you use the ADE with dispersion coefficients as a function of the Peckley number?
Yeah, so that's a good question. So what we did is to keep a constant dispersivity, which is dispersion coefficient divided by pore velocity, but each breakthrough curve has a different dispersion coefficient. So I guess to answer the question is, most likely if you change the dispersivity for each flow rate, you might be able to get a better description. Probably for the sandstone, I don't think you will manage for the carbonate. For the carbonate, you need to introduce some additional equation that describe additional mass transfer processes like diffusion into microporous zone and so on.
Just on that particular, there's some other questions, but for me, follow-up questions. So I'm really interested in this mobile or mobile exchange, be it macro and microporosity or matrix and fractures. So do you think with the work that you're planning to do, we will be eventually able to get a handle on how much heterogeneity there's in the flowing domain versus the stagnant domain? Doesn't matter if it's fractures or matrix or macro and microporosity, because again, this is a really big unresolved issue.
It's a very good question. So there are some elements I think here. So something we're looking at the moment is actually an ability to independently characterize the immobile domains. Let's call them immobile domains. And so there is an interest. So that's obviously, for an imaging point of view, it's a big challenge because you don't see them, right? They're below the resolution. But there are ways that you can try to tackle the problem. So that's one aspect. And the other, I think, with some of the models, like the continuous time random walk, I think they do provide some interesting insight when you play with these different time scales to understand the mobility in the different regions. So the variability. So I like to talk about transition time. So it's not strictly immobile or mobile, but there is just a range of that describe this exchange. So, but you need a lot of data. So I think the direction is really doing these measurements over a wide range of flow rates that allow you really to push the system to the extremes in a way, right? And being able to somehow calibrate these models.
Okay, thank you. Here's some questions from Wilhelmine, and she starts out saying, "Thank you for the nice presentation. I have a slightly different question than the topic of the talk today." She says, oops, sorry, that's Julian's question. What would be the best experimental way to characterize dispersion or mixing of a gas system in sandstone reservoirs?
Yeah, well, you can do, it's a very good question. I think you can do a similar experiment. Actually, we did think about doing some experiments a couple of years ago. You need to think of, so the experiment itself is similar. You can have, again, a tracer experiment that you carry out. You need to think about the way to measure the concentration of the tracer leaving the sample. So what we attempted to do, and we were, I think, partly successful there, is to use a mass spectrometer. And there you for instance, you would have a carrying gas, like, I don't know, helium or nitrogen, and then you inject a pulse of a different species, like CO2 or methane. And the mass spectrometer will be able to detect the concentration change downstream. And then you can use the same models to interpret the experiments.
Thank you. So this is something Wilhelmine can go and test in the labs here then pretty soon. Moving on to you comment on the relationship to potentially in the future to two-phase flow. Susmit has a question, says, "Thank you for the insightful presentation. Kindly clarify what is the impact of water-oil saturation variations during species transport on breakthrough curves and the validation in different porous systems?"
Yeah, that's a question. I would like to answer it as well. You need the experiments there. So essentially, the presence of a second phase, the way I'm thinking about the problem is in two ways. So one way that one could start looking at the problem is to have a second immobile pore space, like a residually trapped, oil phase. And so this basically introduces a new level of heterogeneity because the fluid phase won't be distributed uniformly in your system. So it's almost like, different class of grains being present in your rock. And so depending on the distribution and the extent of the second phase, you will have an effect of your dispersion. And there is very little work in that area, so there is definitely a lot of scope to work there. And the relationship is not, I would say, it's not monotonic. So it's not that you can have a straight line going to, let's say, from no second phase to the other phase, but it goes through a maximum and a minimum, and has to do also with the morphology of the second phase, the way it's distributed. So it's definitely a very interesting problem, but has not been studied to a great extent.
Thank you. And Julian comes up with, again, two-phase flow question, and he says, I love the last bit about matching permeability with a concentration map. Do you think matching the capillary pressure map to permeability map will not work because in a way it's too much information?
Yeah, it's something that we are also, I guess, we are almost there to answer that question, because I think we have now the two pieces of information, because we started with this capillary pressure matching. You know, in sandstone, most likely that the capillary pressure matching will work because we know that J leverage it's quite good, right? So, and J leverage is this function that provides a link between capillary pressure, permeability, and porosity. But in carbonates, then you start again from zero, I guess. And so it's something to explore. I think that there must be a link, because, you know, in a way, some of the parameters of the capillary pressure curve do reflect the morphology of the pore space and the connectivity. But again, it's early days for us, so we're still exploring the option.
Okay. Just thinking, there are no further questions coming through from the audience, but just thinking on the last two questions, and perhaps ask one final one for myself. So, as you said, the two-phase flow has additional complexities, and you're probably not going to get a non-monotonic behavior. So would the next logical step be to look at some basic reactive transport processes to introduce nonlinearities and understand how the system behaves once you get some nonlinear behavior before all hell breaks loose and we have two-phase flow and trapping and all the fun.
No, I agree. Yes, I think the next logical step is to add reactions. I completely agree. And as we know, there are, particularly in the context of CO2 sequestration, you know, these are quite relevant, particularly when you consider carbonates. And so definitely, I think the direction is set. I think we are close to having a good workflow, right, where you can start with your conservative tracers, you have a good understanding of your rock sample, and then you move to some reactive tracer to see what happens. Yeah.
Great. There are no further questions from the audience, but I'm just going to bring up one comment here from Hardy, who's out doing his first ever field trip looking at some real rocks today. So he says, hello to everyone from the Belgium outcrops, being under geology training. Great we can connect in the field. Ronny, Christine, and Sebastian, great to see you. Geology rocks. So we're turning Hardy into a geologist, and he's going to be back next week. So greetings from him. Thanks. Ronny, thank you very much again for a really interesting talk. You're opening the door to lots of fun and interesting science, and I'm really looking forward to seeing what is coming out once you venture into the two-phase flow and the reactive flow side. And I think especially so the link to the lab work is absolutely fascinating. Thank you to the audience for the questions. And Christine, over to you for some final comments announcing the next speaker.
Yes, thanks again, Ronny, for the great talk from my side as well. Very, very interesting. But now I would like to introduce our next week's speaker, which will be Rachel Gavey. She's the founder of the RGC Limited and the co-founder of Sustainable and Environment, Social Governance Strategy and Advice. The title of her talk next week is the diversification of the oil and gas industry, why, how, and future jobs. I think a very important and interesting topic, and I'm sure you will agree with me. So until next week, stay happy, healthy, and tuned into the Geoscience and Geoenergy channel. Bye-bye.
Thank you, everyone. Bye-bye. Thank you.
Bye, everyone. Thank you.